Okay, let's move on to Lesson 3, Flight Instruments. Flight instruments relay critical information about the plane's attitude, its altitude, and speed during every phase of flight. In this lesson, we'll cover how these instruments function and their limitations so that you, the pilot, will have all the information required for safe IFR flight. The majority of the training fleet presents instruments using the conventional six-pack gauges. While newer aircraft now use electronic displays, these older steam gauge instruments fall into 4 general categories based on the systems from which they operate. We'll discuss the pitot-static system, the gyroscopic or vacuum system, the electronic components, and magnetic compass. With us in our studio now is Robert Bremer. Robert's going to be your instructor for this lesson, Flight Instruments. Robert, welcome.
Well, thanks, Matt.
Now, Robert is no newcomer to aviation. His background goes back more than 15 years as an instrument and multi-engine flight instructor. Besides his teaching at Portland State University, he's been presenting ground school lessons for all ratings on video for Stenbach Communications and ASA regularly, and developing and delivering corporate training to global clients. Again, Robert, we appreciate you being with us. Now, before we get underway, tell us a little bit about what you're going to cover.
Well, Matt, thanks for the great introduction. Today we're going to be talking about instruments.
Very good.
You may ask why we need flight instruments. Well, prior to the availability of accurate flight instruments, practical transportation in aircraft was virtually impossible. Flight instruments are essential to conducting safe flight operations, and pilots must have a solid understanding of their operation. In addition to the basic flight instruments required for VFR operations, the airspeed indicator, the altimeter, and the compass, operating under IFR conditions requires gyroscopic instruments, such as a rate of turn indicator, a heading indicator, and an attitude indicator. You also need a slip-skid indicator, a sensitive altimeter adjustable for barometric pressure, and a clock displaying hours, minutes, and seconds, or a digital presentation. We'll be covering these instruments in detail, how they work and how to use them. We also cover what you need to do if one of the instruments fails during your flight.
Robert, sounds fascinating. You've got a lot of information to cover there. Let's get started.
Oh, we do. We're going to get started now. I'll see you guys in the classroom.
We'll cover these topics: airspeeds, altitudes, altimeter, vertical speed, attitude indicator, turn coordinator, heading indicator, magnetic compass, slave gyro, instrument errors, instrument skills, attitude flying, and unusual attitudes. Okay, let's move into the classroom with our first topic, airspeeds. Join your instructor now.
Hi, I'm Robert Bremer, your instructor for this lesson on flight instruments. Flight instruments are the key component of IFR flight. In fact, flight in IMC would be impossible without these instruments. The first instrument we'll discuss is the airspeed indicator. It's part of the pitot-static system, which we'll discuss in greater detail later. Here we have a simplified diagram of the pitot-static system to which the airspeed indicator is connected. The airspeed indicator is connected directly to the pitot tube. So let's take a look at the inner workings of an airspeed indicator. The ram air enters the pitot tube and pressurizes this diaphragm. The diaphragm drives airspeed indicator hands through a mechanical coupling consisting of a long lever and this sector gear. So let's take a look at some common types of airspeed indicators that are found in general aviation airplanes. First is a true airspeed indicator, like the one you see here. A true airspeed indicator allows the pilot to correct indicated airspeed for non-standard temperature and pressure. Next is a maximum allowable airspeed indicator with a movable pointer indicating the never exceed speed, which changes with altitude. And finally, we have a Mach meter, which shows the ratio of the speed of sound to the true airspeed the aircraft is flying. So let's take a look at some definitions of a typical airspeed indicator. We'll take a look at a closer look at the color coding. You'll notice that there's a series of color-coded arcs on the airspeed indicator. There's a white arc, green, yellow, and then we have this red line right here. These are airspeed limitation ranges or operating limits of your airplane. Depending upon what airplane you fly, the arcs may shift to different airspeeds, but you'll see these colored arcs on each and every airplane you fly. Indicated airspeed is that speed that's read directly from the airspeed indicator. Now, airspeed that is corrected for installation and instrument error is called calibrated airspeed. And true airspeed is calibrated airspeed that's corrected for variations in temperature and pressure. And finally, the Mach number is that ratio of true airspeed to the speed of sound. Let's study airspeed limitations. The white arc, which you see right here, represents the flap operating range. At the bottom of the white arc, or at the lower speed, is the airspeed limitation called VSO. The V stands for velocity, or speed, and in this case, the S stands for stalling, and the O stands for a certain configuration. In this case, that configuration is the lowest possible airspeed you can have with the flaps and the landing gear down, or in the landing configuration. Below this airspeed, in the landing configuration, the airplane will stall. Now, we also have VS1. We know that V is for velocity and S is for stall, but this is configuration 1. This means with the flaps up or in a clean configuration. If you fly below this airspeed and your flaps are still in the up position, the airplane will stall. Remember this, VS1 is the stalling speed in a clean configuration, or stuff in. And VSO is the stalling speed in a landing configuration with flaps and gear down, or stuff out. Now, at the top, or the higher end of the white airspeed arc, is another limitation called VFE. VFE, V is for velocity, F is for flaps, and E is for extension. This is the maximum speed at which you can fly with the flaps extended. We also have this green arc, and the green arc represents the normal operating range. At the top of the green arc, at the higher end, we have VNO, and this is really the highest airspeed you should fly under most operating parameters. You can, from time to time, fly into the yellow arc over here if the air is very smooth. But just like a street light, remember, yellow means caution. If the air is bumpy, you want to reduce your speed to fly in the green arc. Now, like we were saying, the yellow arc represents caution. Operating in this range requires caution, and as mentioned earlier, you should only fly at these speeds in smooth air. At the very top of the yellow arc is the red line, right here. This is V and E. V for velocity, N for never, and E for exceed. Never exceed speeds above this red line can be very dangerous. If you fly above this speed, you risk the likelihood of structural damage to the airplane. There are also some airspeed limitations that are not marked on the airspeed indicator, but you need to know them just the same. VA is maneuvering speed. Maneuvering speed is that speed at which you may move the flight controls to their maximum fore and aft deflection and not produce any structural damage to the airplane. VA, or maneuvering speed, can be found in the pilot's operating handbook for the particular airplane that you're flying. Another airspeed limitation not depicted on the airspeed indicator is VLE. VLE is the maximum landing gear extension speed. This is the maximum speed at which you can safely lower the landing gear if you have aircraft with retractable landing gear. Again, this speed is found in the pilot's operating handbook. Now, next is VX speed. VX is the best angle of climb speed. And VY is the best rate of climb speed. Let's take a look at an example. Now, here our airplane is rolling for departure. but you'll notice there's a group of trees at the end of the runway. If you have an obstruction at the end of the runway, you need to make sure you can climb out at Vx, the best angle of climb speed. This airspeed allows the airplane to gain the greatest amount of altitude in a given distance. Now here's an example of Vy speed. When your objective is to gain the most altitude over a given unit of time, you use Vy. Generally, once you've cleared the obstructions, you can use Vy, the best rate of climb.
Okay, let's take a break right now for a review question. This one, what information does a Mach meter present? Have a look at A, B, or C as your answer. Well, the answer in this case is A. The Mach meter indicates the ratio of aircraft true airspeed to the speed of sound at flight altitude. Okay, let's move along to another topic. And we're at altitudes. Back into your classroom to join your instructor.
Our flight altitudes are an important aspect in both VFR and IFR operation. Aviators define altitudes based on a number of factors determined by both physical properties and regulations. In this section, we'll study types of altitudes. Let's talk about the various types of altitudes. Now, here's an overview of the various altitudes you need to know. There is indicated altitude, and then we have pressure altitude, followed by true altitude, density altitude, and finally, absolute altitude. Let's cover these in greater detail. We'll start with indicated altitude. Indicated altitude is simply the altitude that's shown on the face of your altimeter. Remember this, atmospheric pressure decreases an inch for every 1,000 foot altitude increase. So if our altimeter is set to 29.15 inches and a new altimeter setting of 29.85 inches is entered, representing a change of 0.7 of an inch, this equals a change in altitude of 700 feet. Now, here's a review of pressure effects. Suppose we're flying along and our altimeter is set to 29.92 inches. We get a call from the tower, or we talk to FlightWatch and they say our altimeter setting should be 28.92. That's a decrease of 1 inch of mercury. So we have a change in altitude of 1,000 feet. In the first case, the local pressure and altimeter setting agree with a true and indicated altitude of 4,000 feet. As the aircraft flies toward the lower pressure, but without resetting the altimeter, the indicated altitude and true altitude differ by 1,000 feet. So you want to remember the wise old saying, when flying from high to low, look out below. Now, a correctly calibrated pressure altimeter indicates true altitude above mean sea level, or MSL, when operating within the International Standard Atmosphere, or ISA, parameters of pressure and temperature. Non-standard pressure conditions are corrected by applying the local area altimeter setting. Next, let's take a look at true altitude. True altitude is the vertical distance of the airplane above mean sea level, or MSL. Airports, terrain, and obstacle elevations on aeronautical charts are true altitudes. Density altitude is pressure altitude corrected for non-standard temperature, which is 59 degrees Fahrenheit. Since you'll often be flying in non-standard conditions, you need to know and understand density altitudes and how they affect your airplane's performance. Absolute altitude is the vertical distance of your airplane above ground level, or AGL. When the aircraft is flying in air that is warmer than standard, the air is less dense and the pressure levels, well, they're further apart. When the aircraft is flying at an indicated altitude of 5,000 feet, the pressure level for that altitude is higher than it would be in air at standard temperature, and the aircraft is also higher than it would be if the air were cooler. If the air is colder than standard, it is denser, and the pressure levels are closer together. True altitude is higher than indicated altitude whenever the temperature is warmer than ISA. Now in this example, let's assume we are flying in temperatures outside of ISA parameters. Here we're flying with an indicated altitude of 11,000 feet. The local pressure remains at the standard condition of 29.92 inches. We're flying in warmer than standard air. Because the air is less dense and the pressure levels are further apart, the altimeter reads 10,000 feet, but the true altitude is 11,000 feet. Next, we fly into an area where the temperature is colder than standard. Because the air is denser and the pressure levels are closer together, the altimeter reads 10,000 feet, but the true altitude is 9,000 feet. Now we have a table to look at. This table that you see here is derived from International Civil Aviation Organization, or ICAO data. The cold temperature-induced altimeter error may be significant when considering obstacle clearances when temperatures are well below standard. You may want to increase your minimum terrain clearance altitudes with a corresponding increase in ceiling from the normal minimum when flying in extreme cold temperature conditions. Now, if compensation is applied, ATC must be informed that the aircraft is not flying the assigned altitude. Otherwise, vertical separation from other aircraft could be reduced, creating a potentially very hazardous situation. Under extremely cold conditions, pilots may need to add an appropriate temperature correction determined from the chart to charted IFR altitudes to ensure terrain and obstacle clearance with the following restrictions. Altitudes specifically assigned by Air Traffic Control, or ATC, such as maintain 5,000 feet, shall not be corrected.
Contact 5 miles east of McMinnville, Portland, altimeter 3019er.
3019er, thank you. 9 Golf Romeo.
Welcome. Verify your altitude again, please.
We're just coming up on 4,000, 9 Golf Romeo.
Thank you.
Assigned altitudes may be rejected if the pilot decides that low temperatures pose a risk of inadequate terrain or obstacle clearance. As a pilot, you must advise ATC of any applied corrections.
Okay, let's take a look at a couple review questions this time. First, under what conditions is pressure altitude and density altitude the same value? Which of these three? Your answer, of course, is A. Density altitude is pressure altitude corrected for non-standard temperature. Under standard atmospheric conditions, each level of air in the atmosphere has a specific density, and under standard condition, pressure altitude and density altitude identify the same level. Okay, let's take that second question. Under what condition will true altitude be lower than indicated altitude with an altimeter setting of 29.92 inches of mercury? Which of these, A, B, or C? The correct answer here is B, in colder than standard air temperature. Effects of non-standard conditions can result in a difference of as much as 2,000 feet between true and indicated altitude on a cold day. So there you have it. All right, tackling yet another topic here. We are going to go down for the altimeter. Back to your instructor in your classroom.
In this section, we study the altimeter as we find it in your instrument panel. It displays the altitude at which the aircraft is actually located, flying or otherwise. We'll learn its physical characteristics and how it's used. Next, let's take a look at the altimeter. The altimeter is part of the pedostatic system. The altimeter shows your height above mean sea level. There are a number of hands on the altimeter, which we'll explain in a moment. Here's an inside view of the altimeter. The static port, which we see right over here, provides ambient pressure, or the static pressure next to the airplane, for the altimeter. Right here, the aneroid acts like a bellows. It's mechanically coupled to the altimeter pointers. The pointers generally contain a 100, 1,000, and 10,000 foot hand, and there's a barometric scale adjustment knob which adjusts the altimeter setting in the Colesman window. The crosshatch flag that you see right down here, that warns the pilot of low altitudes. Now, here are two typical altimeters, the three-pointer style and the drum-type altimeter. Each provides the same information. The drum-type altimeter is most often found on larger and more complex airplanes. Let's take a closer look at the altimeter. This little cut right here is called the Colesman window, and it displays the altimeter setting. For example, if you departed from a controlled airport that has either a tower, ASOS, or ATIS information, you dial the altimeter setting, you dial it in right here, and you use this little knob right here. If you're departing from an airport that does not have these services, you turn the dial to the field elevation from which you are departing. This will give you a fairly accurate barometric pressure indication. Now, to pre-flight the altimeter, the current reported altimeter setting should be set in the Colesman window. You would note any variation between the known field elevation and the altimeter indication. If the variation exceeds plus or minus 75 feet, the accuracy of the altimeter is questionable, and the problem should be referred to an appropriately rated repair station for evaluation and possible correction. Let's take a closer look at the altimeter pointers. Aside from incorrectly setting an altimeter, one of the most common errors is just simply misreading it. Now, just like a wristwatch, we have three hands. But instead of having hours, minutes, and seconds, in this case we have a 10,000 foot indicator, we have a 1,000 foot, and we have a 100 foot hand. This 10,000 foot hand right there is not yet to the 1, so we have less than 10,000 feet. Now, take a look at our 1,000 foot indicator. We're above 2, and we have almost 500 here, so we're close to about 2,500 feet altitude above mean sea level. When you're flying above 18,000 feet, which would be an IFR operation, the altimeter should be set to 29.92 inches. This ensures all aircraft will be flying with the same altimeter setting, thus ensuring separation. Now, check out this graphic. Remember, 1 inch of altimeter change equals 1,000 feet of altitude change. In this example, the altimeter setting is changed from 30.11 to 29.96, which is a change of 0.15. So the altitude change is 0.15 times 1,000 feet equals 150 feet.
We are extremely pleased to have Steve Kastner in the studio with us today. Now, Dr. Kastner is a research scientist at NASA Ames Research Center in California. He has an airline transport pilot certificate with type ratings in the Boeing 737 and the Cessna Citation. He is also a Gold Seal certified flight instructor. Now, for the past 15 years, Steve has been involved in researching the way pilots learn to use advanced cockpit systems, such as GPS, moving maps, and autopilots, that sort of thing, and how these systems can affect pilot awareness, workload, and the types of errors that pilots make. Steve, we appreciate you being with us.
Oh, thanks. Good to be here.
Now, number one question. Many of today's pilots are transitioning from steam gauge instrumentation to this, the glass cockpit. How is flight training evolving as a result of that?
Well, I think there's two schools of thought here. One school believes we should be teaching pilots to use these systems that we're now seeing in the cockpit and to put their trust in them. Another school believes we should be teaching those systems in addition to all of the old navigational skills that pilots learned in yesteryear: time, distance, rate calculations, fuel calculations, and whatnot. So depending on your frame of mind here, some people believe that flight training is getting simpler and some people believe it's getting more complex.
Now, is there a different mindset that pilots need to use to operate an automated cockpit in addition to the basic stick and rudder skills?
Yeah, absolutely. The biggest challenge I see here is learning to put yourself in the role of being a manager of information rather than a doer of everything. and developing the ability to intelligently follow along as the systems do the work that you've delegated to them.
Now, is it possible for a private pilot to move back and forth between the conventional six-pack and glass cockpit without compromising his skills?
Yeah, absolutely. I think the research is really clear on this topic. Any skill that you want to maintain proficiency at, you simply just have to practice regularly. That's certainly true of working with a GPS or autopilot. You've got to maintain proficiency with the button pushes and whatnot. And the same thing with scanning a six-pack panel. Basically, the bottom line is use it or lose it. Whatever you practice on a regular basis, you'll continue to be good at.
Steve, what's the basic idea behind the primary flight display?
Well, the primary flight display is easily one of the more interesting additions to the new cockpit. The first thing you notice about a PFD, or primary flight display, is that it's able to pack more information into a smaller space. What happened here is, as we started adding new systems to the cockpit, we couldn't have pilots craning their necks in all directions to gather the information they needed. So the PFD really integrates everything into one complete picture.
Well, now, did you have any difficulty yourself transitioning from round gauges to vertical tapes?
Well, tape displays are the one thing that I see students having trouble with initially. We have to remember how valuable those old round dial gauges were. For example, the altimeter. I could be looking off in a different direction and notice out of the corner of my eye if that big white needle started to lean to one direction or another, and instantly know if I was drifting off my altitude. With a tape display, it certainly seems I've got to stare a little closer at that. It's not so obvious when my 5,000 changes to 5,080 or something. It just requires us to look more directly at it and a little more closely. So what I see is students, after a few hours of practice, eventually get into the habit, and the altitude deviations just go away.
Okay, let's take on another pair of review questions. First, when an altimeter is changed from 30.11 inches of mercury to 29.96 inches of mercury, in which direction will the indicated altitude change, and by what value? Which of these three, A, B, or C, is correct? Well, in order to get there, we have to do a little math. Given that 1 inch of mercury of altimeter change equals 1,000 feet of altitude change, if we do our math, the altimeter setting change, we take 31.11 inches away from 29.96 inches, we arrive at a negative 0.15 inches. We multiply that times our 1,000 feet of altitude change, we get a negative 150 feet. We go back to our question, and our correct answer, of course, is B. The altimeter will indicate 150 feet lower. All right, let's move along to the second one. En route at flight level 290, the altimeter is set correctly but not reset to the local altimeter setting of 30.57 inches of mercury during descent. If the field elevation is 650 feet and the altimeter is functioning properly, what is the approximate indication upon landing? Okay, which of these three? I'm going to have to do some more math. Given 1 inch of mercury of altimeter change equals 1,000 feet of altitude change, and given the altimeter must be set correctly to 29.92 inches above 18,000 feet MSL, well, if we do our math, we take 29.92 inches away from 30.57 inches, we come up with 0.65 inches. Multiply that by our 1,000 feet, we get 650 feet. Our field elevation of 650, we take that away from it, so our answer is C, sea level. Given the fact that the altimeter was not set to the field elevation pressure, the altimeter will read sea level or 0 feet. Okay, let's pick up one more question here. We're going to show you altimeter 2 in just a second, but altimeter 2 will indicate which of these three answers, A, B, or C. Here's your altimeter. Okay, one hand reads in tens of thousands of feet. This one reads in thousands of feet. The bottom hand there, hundreds of feet. So what is the indication here? 14,500 feet, correct. Let's go back to our question. The answer then is C. It should be 14,500 feet, and that is correct. Okay, moving on to another topic. Vertical speed is the topic. We'll go back to your classroom and your instructor.
Next up is the VSI, or vertical speed indicator. It's also called a vertical velocity indicator, or VVI, and was formerly known as a rate of climb indicator. It's a rate of pressure change instrument that gives an indication of any deviation from a constant pressure level. The vertical speed indicator, or VSI, is also part of the pedostatic system. It's connected to the static side of the system. The VSI, formerly known as a rate of climb indicator, is a rate of pressure change instrument that gives an indication of any deviation from a constant pressure level. The vertical speed indicator measures the rate and climb or descent in hundreds of feet per minute, 500, 1,000, 1,500, or minus 500, minus 1,000, minus 1,500, and so on. Although not required by regulation to be on board, the VSI is commonly found on instrument-equipped airplanes. To pre-flight the VSI, you would check to make sure that there's a 0 reading prior to takeoff. If it's indicating a climb or descent, you would note the error and apply it to the readings in flight. The VSI, or rate of climb indicator, is a very sensitive altimeter with a calibrated leak in the case. Inside the instrument case is an aneroid very much like the one you would have in an airspeed indicator. Now, both the inside of this aneroid and the inside of the instrument case are vented to the static system. But the case is vented through a calibrated orifice that causes the pressure inside the case to change more slowly than the pressure inside the aneroid. It uses the static source as the sensor. As the aircraft ascends, the static pressure decreases. The pressure inside the case compresses the aneroid, moving the pointer upward, showing a climb and indicating the rate of ascent in number of feet per minute, or FPM. When the aircraft levels off, the pressure no longer changes. The pressure inside the case becomes equal to that inside the aneroid, and the pointer returns to the horizontal or 0 position. When the aircraft descends, the static pressure increases and the aneroid expands. This moves the pointer downward, indicating a descent. The pointer indication in a VSI lags a few seconds behind the actual change in pressure. However, it's more sensitive than an altimeter, so it's useful in alerting the pilot if an upward or downward trend is going on, thereby helping to maintain a constant altitude.
Welcome back. Let's take on another review question for you. You check the flight instruments while taxiing and find that the vertical speed indicator, or VSI, indicates a descent of 100 feet per minute. In this case, you would take which of these actions, A, B, or C? And your answer? B. The VSI should indicate 0 plus or minus 100 feet on the ground. Okay, moving along to another topic. This time out, attitude indicator. We ask you to join your instructor in the class.
Flight without reference to a visible horizon can be safely accomplished by the use of gyroscopic instrument systems and the 2 characteristics of gyroscopes, which are rigidity and precession. These systems include attitude, heading, and rate instruments along with their power sources. These instruments include the attitude indicator, turn coordinator, and the heading indicator. A gyroscope, or gyro, is a small wheel with its weight concentrated around the periphery. When this wheel is spun at very high speeds, it becomes rigid and resists tilting or turning in any direction other than around its spin axis. It takes on a property called rigidity in space. Because of this effect, the gyro does not tip but stays upright. When the gyroscope is mounted inside a gimbal device, that gimbal mechanism is moved around its 3 axis points. The gyro will still stay rigid. When this gyro is mounted in an aircraft, the gyro remains rigid in space and the aircraft rotates around it. In the airplane, the instrument will have a constant reference in space as the airplane pitches, rolls, and yaws around it. Attitude and heading instruments operate on the principle of rigidity. Now, rate indicators, such as turn indicators and turn coordinators, operate on the principle of precession. The gyro precesses or rolls over proportionate to the rate the aircraft rotates about one or more of its axes. Here is a spinning gyro. As force is applied to this point right here with the red dot, the force advances 90 degrees. And that's where it's applied. And this causes the gyro to tilt in that direction. Pneumatic gyros are driven by a jet of air impinging on buckets that are cut into the periphery of the wheel, as shown on this turn and slip indicator. On many aircraft, this stream of air is obtained by evacuating the instrument case with a vacuum source and allowing filtered air to flow into the case through a nozzle to spin the wheel. Aircraft that do not have a pneumatic pump to evacuate the instrument case can use Venturi tubes that are mounted on the outside of the aircraft, similar to the system that we see here. Air flowing through this Venturi tube accelerates in the narrowest part, and according to Bernoulli's principle, the pressure drops. Now that location right up here, up there at the point of the Venturi, is connected to the instrument case by a piece of tubing. The two attitude instruments operate on approximately 4 inches of mercury of suction. The turn and slip indicator, however, only needs 2 inches of mercury, so a pressure reducing needle valve is used to decrease the suction. Air flows into the instruments through filters built into the instrument cases. Now in this system here, we have a problem. Ice can clog the Venturi tube and stop the instruments when they're most needed. So here's a typical vacuum pump system. This vacuum pump pulls air into and out of the gyro instruments. The vacuum pump is driven by the engine of the airplane. The air is pulled through a filter, and it comes out of the filter and then moves into the heading and attitude indicators. The air flows through the instruments and is evacuated through a regulator. The regulator maintains a constant rate of vacuum pressure moving into and through these instruments. This gauge right here that you see on your instrument panel indicates how much vacuum pressure is applied to these instruments and being generated by your vacuum pump. After the air moves from the regulator and goes into the pump, it's vented overboard the airplane. Now, there are other types of systems used in other aircraft. In some systems, instead of a vacuum, pressure drives the instruments. There's a pressurization system which is used on Bonanza aircraft as an example. A third type of gyro-driven instrument that's come out in recent years doesn't even use any of this. It's called a solid-state gyro. What we see here is the business end of our attitude indicator, or artificial horizon. This is the face of the instrument. We have a miniature airplane, and it has wings, and they're indicating along this horizon. You can adjust the airplane up and down on the horizon with this little knob. Turning the knob allows you to align the miniature airplane with the horizon in the instrument. A pre-takeoff check verifies that the horizon bar stabilizes within 5 minutes and does not dip more than 5 degrees during taxiing turns. These marks up here indicate bank angle from 0 degrees all the way over to a full 90 degrees of bank. Now, that's the attitude indicator, or artificial horizon. The attitude indicator provides an immediate, direct, and corresponding indication of any change of aircraft pitch and bank attitude. This pitch and bank depiction is in relation to the natural horizon. It's the pilot's primary instrument during transitions of pitch. The attitude indicator is subject to some errors that you need to know about. These are: following a 180-degree turn, it indicates a slight climb and bank in the opposite direction. That's called turn error. Now, following a 360-degree turn, this error cancels itself out and it's not apparent. Also, during acceleration, the horizon bar moves down, indicating a climb. This is acceleration error. During deceleration, the horizon bar moves up, indicating a descent. That's deceleration error. Now let's take a look at some examples. First, there's the indication before turn. Then there's the indication during a 180-degree turn. And here is the indication after 180 degrees of turn, slight climb and turn in the opposite direction. And this here is the indication before accelerating in level flight. And lastly, here is the indication during acceleration in a slight climb.
Okay, let's take care of a couple of review questions for you. During normal operation of a vacuum-driven attitude indicator, what attitude indication should you see when rolling out from a 180-degree skidding turn to straight and level coordinated flight? Which of these is correct? And our answer is C. The miniature aircraft will indicate a turn in the direction opposite the skid. Okay, very good. Let's tackle another one here. If a 180-degree steep turn is made to the right and the aircraft is rolled out to straight and level flight by visual reference, the attitude indicator A, B, or C? And your answer is C. Attitude indicators are free from most errors, but there is a possibility of a small bank angle and pitch error after a 180-degree turn. Okay, let's move along. Another topic. This one, turn coordinator. Back to your classroom.
The next instrument that uses a gyroscope is the turn indicator. Before we discuss the turn coordinator instrument in detail, it's a good time to review the turning forces. Remember, an airplane turns because of the horizontal component of lift. The greater the horizontal lift, the greater the rate of turn. In a turn, the angle of attack must be increased to maintain altitude. With reduced airspeed, you would decrease the bank angle or increase the angle of attack to maintain level flight. In a constant bank, airspeed increase results in a decrease in turn rate and an increase in radius. Check this animation. As the airplane enters the turn, a number of force vectors are created. There's the vertical component of lift. There's a horizontal component of lift, followed by the centrifugal component of lift. These forces combine to create the resultant lift vector. Finally, remember that the load factor is the ratio between the resultant lift and the aircraft's weight. Here's a cutaway view of a typical turn coordinator. Note the canted gyro and rotation, the gimbal, and the face of the turn coordinator. A turn coordinator operates on precession, the same as the turn indicator, but its gimbal frame is angled upward about 30 degrees from the longitudinal axis of the aircraft. This allows it to sense both roll and yaw. Therefore, during a turn, the indicator first shows the rate of banking and once stabilized, the rate of turn. The bezel of the instrument is marked to show wings level flight and bank angles for a standard rate turn. It's gyroscopically operated, designed to show roll rate, rate of turn, and quality of turn. It acts as a backup system for the vacuum-powered attitude indicator. Before engine start, the turn needle should be centered. During a taxiing turn, the needle indicates a turn in the proper direction and the ball shows a skid. The turn coordinator provides both yaw and bank information. The little miniature airplane provides only an indirect indication of roll, responding with the airplane's banking action in some cases even before the turn can actually commence. However, in this case, the ratio of the turn is not 1-to-1 with the horizon like it is on the attitude indicator. This means that in a 30-degree bank turn, the miniature airplane will show a bank on the turn coordinator, but it may not show up as a 30-degree bank. At the bottom of the instrument is a little fluid-filled tube and ball. A turn coordinator does not sense pitch. This is indicated on some instruments by placing the words "no pitch information" on the dial. Now the inclinometer down here is called a coordination ball, which shows the relationship between the bank angle and the rate of yaw. In a coordinated turn, horizontal lift and centrifugal force are equal. In a skid, the rate of turn is too great for the angle of bank and the ball moves to the outside of the turn. To correct this condition, increase the bank or decrease the rate of turn. The turn is coordinated when the ball is in the center, between the marks. The aircraft is skidding when the ball rolls toward the outside of the turn and is slipping when it moves towards the inside of the turn. Now, a standard rate of turn is 3 degrees per second. It takes 1 minute to complete a 180-degree turn. A half standard rate turn is 1/2 degree per second. That takes 4 minutes to complete a 360-degree turn, or it takes 60 seconds to complete a 90-degree turn. The turn and slip indicator is a small gyro spun either by air or by an electrical motor. Note the horizontal gyro, gyro rotation, gimbal rotation, the standard rate turn index, and the inclinometer. The gyro is mounted in a single gimbal with its spin axis parallel to the lateral axis of the aircraft and the axis of the gimbal parallel with the longitudinal axis. The turn and slip indicator indicates yaw, but not roll.
Okay, this is a good time to review with a couple of questions what you just learned. If a standard rate return is maintained, how long would it take to turn 180 degrees? Which of these is true and correct, A, B, or C? The answer is A. 3 degrees per second times 60 seconds equals 180 degrees. All right, question number 2. What indication is presented by the miniature aircraft of the turn coordinator? Which of these is correct? Your answer? A. The miniature aircraft depicts an indirect indication of the bank attitude. Okay, selecting a new topic. We're down to heading indicator, and we're back in your classroom for that topic.
Next up, the heading indicator. The heading indicator is the final gyroscopic instrument. It basically provides the same information as the magnetic compass, but in a much better way. It does, however, require that it be set to match the magnetic compass. Here we go. The last gyro instrument is the heading indicator. It looks very similar to a compass. The heading indicator shows the direction the nose of the airplane is heading. In this case, we're heading 341 degrees. The heading indicator is much easier to read than a magnetic compass using a heading adjustment knob. The heading indicator consists of a pictorial representation of an airplane that's moving along the compass rose. Assuming the heading indicator has been aligned with your magnetic compass, it will indicate the magnetic heading under the nose of the airplane. But unlike the magnetic compass, the heading indicator is not a true direction-seeking instrument. This means it doesn't have a north reference unless it has a remote compass system to do that automatically. You must set it to agree with the magnetic compass. The heading indicator also has a tendency to drift by a force called gyroscopic precession. Frictional forces within the gyro system cause the heading indicator to drift from its original alignment with magnetic north. To receive accurate indications during flight, you need to occasionally realign the heading indicator with the magnetic compass to counteract gyro precession. Now, some instruments precess quicker than others. You need to check these every 10 or 15 minutes in straight and level, unaccelerated flight. The heading indicator should precess no more than about 3 degrees every 15 minutes. All gyro instruments must be checked prior to flight. You would turn on electrical power before engine start and check for proper operation and unusual noise.
Okay, back into the studio for a review question. What pre-takeoff check should be made of a vacuum-driven heading indicator in preparation for an IFR flight? Which of these is your correct answer? And our answer is A. After 5 minutes, set the indicator to the magnetic heading of the aircraft and check for proper alignment after taxi turns. Very good. Moving along, yet another topic. We are down to magnetic compass. We ask you to join your instructor in the classroom.
The last instrument we're going to study is the magnetic compass. The magnetic compass is not a pressure-driven or gyro-powered instrument, but it is perhaps the most important instrument there is. You have to know where you're going. The magnetic compass does, however, suffer from error tendencies. As you know, the Earth has geographic and magnetic poles. Lines of magnetic force stretch between the north and the south magnetic pole. These lines of force are sensed by the magnetic compass. The magnetic compass points towards magnetic north. All general aviation aircraft are equipped with a magnetic compass. The float and card assembly has a hardened steel pivot in its center that rides inside a special spring-loaded hard glass jewel cup. The buoyancy of the float takes most of the weight off the pivot, and the fluid damps the oscillation of the float in the card. This jewel and pivot type mounting allows the float freedom to rotate and tilt up to approximately 18 degrees angle of bank. At steeper bank angles, the compass indications are erratic and unpredictable. The compass housing is entirely full of compass fluid. To prevent damage or leakage when the fluid expands and contracts with temperature changes, the rear of the compass case is sealed with a flexible diaphragm or with a metal bellows in some compasses. The magnets align with the Earth's magnetic field, and the pilot reads the direction on the scale opposite the lubber line, which is this vertical line right here. A compensator assembly mounted on the top or the bottom of the compass allows an aviation maintenance technician, or AMT, to create a magnetic field inside the compass housing that cancels the influence of local outside magnetic fields. This is done to correct for deviation error. The compensator assembly has two shafts with ends that have screwdriver slots that are accessible from the front of the compass. Each shaft rotates one or two small compensating magnets. The end of one shaft is marked EW, and its magnets affect the compass when the aircraft is pointed east or west. The other shaft is marked NS, and its magnets affect the compass when the aircraft is pointed north or south. Now, next up are compass errors. Let's start with acceleration errors. First, assume that you're in the northern hemisphere and the airplane is on an east to west heading. The compass will swing to the north while you accelerate and then return to the correct heading. If the aircraft accelerates on a heading of east, the inertia of the weight holds its end of the float back and the card rotates towards the north. As soon as the speed of the aircraft stabilizes, the card swings back to the east indication. If, while flying on this easterly heading, the aircraft decelerates, the inertia causes the weight to move ahead and the card rotates towards south until the speed again stabilizes. When flying on a heading of west, the same things happen. Inertia from acceleration causes the weight to lag and the card rotates towards the north. When the aircraft decelerates on a heading of west, inertia causes the weight to move ahead and the card rotates towards south. If you're decelerating on the same east to west heading, the compass swings to the south and then returns to the correct heading after deceleration. So there's an acronym for this. Remember this, ANDS, A-N-D-S, which stands for accelerate to the north, decelerate to the south. It occurs only on easterly or westerly headings. The compass will indicate correctly when accelerating on north or south headings. Next, there are turning errors. The lines of magnetic flux leave the Earth at the magnetic North Pole and enter at the magnetic South Pole. At both locations, the lines are perpendicular to the Earth's surface. At the magnetic equator, the lines are parallel with the surface. The magnets in a compass align with this field. And near the poles, they dip or tilt. They tilt the float in the card. The float is balanced with a small dip compensating weight, so it stays relatively level when operating in the middle latitudes of the northern hemisphere. This dip along with this weight causes two very noticeable errors: northerly turning error and acceleration error. The pull of the vertical component of the Earth's magnetic field causes northerly turning error, which is apparent on a heading of north or south. When an aircraft flying on a north heading makes a turn toward east, the aircraft banks to the right. This causes the compass card to tilt to the right. The vertical component of the Earth's magnetic field pulls the north-seeking end of the magnet to the right, and the float rotates, causing the card to rotate toward west, the direction opposite the direction the turn is being made. This northerly turning error is based on the aircraft heading north. The compass will want to remain pointing north towards the North Pole when turning away from a northerly heading. The compass will lag or possibly even indicate a turn in the opposite direction during the first part of the turn. When you reach an east or west heading, it catches up and reads correctly. But as you continue with a turn to the south, the compass starts to race ahead of that turn. In fact, to roll out on a south heading, you have to turn past the heading on the compass, overshooting a bit to the north. So there's an acronym for this. Just remember OSUN, which stands for overshoot south, undershoot north. In the mid-latitudes, maybe as much as 30 degrees is reasonable for overshoot or undershoot when turning to the north or south heading. Again, to summarize, when turning to the south, the compass indication will lead. When turning to the north, the compass indication lags. Deviation is the compass error caused by magnetic disturbances from electrical and metal components in the aircraft. The correction for this error is displayed on a compass correction card placed near the magnetic compass in the aircraft. Variation is the angular difference between the true or geographic poles and the magnetic poles at a given point. The compass magnet is aligned with the magnetic poles, while aeronautical charts are oriented to the geographic poles. The variation must be taken into consideration when determining an aircraft's actual geographic location. It's indicated on charts by isogonic lines, and you see them here. Those isogonic lines are not affected by the airplane's heading. Many airports have a compass rose painted on a specific place on the airport's surface, allowing for compensation of deviation errors. A compass correction card prepared by the pilot operator provides heading correction caused by variation and or deviation, and it could look like this here. The vertical card magnetic compass, which we see right here, is an improvement over the fluid-filled magnetic compass. The floating magnet type of compass not only has all the errors just described, but also lends itself to confused reading. It's easy to begin a turn in the wrong direction because its card appears backward. Not so with the vertical compass. The vertical card magnetic compass eliminates some of the errors and confusion. The dial of this compass is graduated with letters representing the cardinal directions, north, east, south, and it's got numbers every 30 degrees and marks every 5 degrees. The dial is rotated by a set of gears from the shaft-mounted magnet, and the nose of the symbolic airplane on the instrument glass represents the lubber line for reading the heading of the aircraft from the dial. Eddy currents induced into an aluminum damping cup damp any oscillation of the magnet.
Back for another review question. When flying in the northern hemisphere, if an aircraft is accelerated or decelerated, the magnetic compass will normally indicate which of these, A, B, or C? Your answer is B. While on an east or west heading, an increase in airspeed or acceleration will cause the compass to indicate a turn toward the north, and a deceleration will cause the compass to indicate a turn toward the south. If on a north or south heading, no error will be apparent because of acceleration or deceleration. Remember, ANDs. Accelerate north, decelerate south. Okay, let's move along to a new topic. This one, slaved gyro. Back to your instructor in the classroom.
The slave gyro system was developed to compensate for the errors and limitations of the older type of heading indicators. There are two types of indicators installed in general aviation aircraft. The one on the left, shown here, is an HSI, or horizontal situation indicator. The example shown on the right is an RMI, or radiomagnetic indicator. Both indicators are synonymous with a pictorial navigation indicator. The two panel-mounted components of a typical system are the pictorial navigation indicator, the slaving control and compensator unit, and a remote magnetic sensor, also referred to as a flux gate compass sensor. The slaving meter indicates any differences between the displayed heading and the magnetic heading. A right deflection indicates a clockwise error of the compass card. A left deflection indicates a counterclockwise error of the compass card. In the free gyro mode, depressing the clockwise manual heading drive button rotates the compass card to the right. Depressing the counterclockwise heading drive button rotates the compass card to the left. The flux gate compass that drives the slave gyro uses the characteristic of current induction. The flux valve is a small segmented ring made of soft iron that readily accepts lines of magnetic flux. An electrical coil is wound around each of the three legs to accept the current induced in this ring by the Earth's magnetic field. A coil wound around the iron spacer in the center of the frame has 400 Hertz alternating current, or AC, flowing through it. During the times when this current reaches its peak, twice during each cycle, there is so much magnetism produced by this coil that the frame cannot accept the lines of flux from the Earth's field. But as the current reverses between the peaks, it demagnetizes the frame, so it can accept the flux from the Earth's field. As this flux cuts across the windings in the three coils, it causes current to flow in them. These three coils are connected in such a way that the current flows in them changes as the heading of the aircraft changes. The three coils are connected to three similar but smaller coils in synchro inside the instrument case. This synchro in turn rotates the dial on the indicator.
Okay, let's take a look at a review question on this topic. When using the slaved gyro system and when the system is in the free gyro mode, depressing the clockwise CW manual heading drive switch will rotate the remote indicating compass card to the A, B, or C. Your correct answer is A. When the system is in the free gyro mode, depressing the clockwise CW manual heading drive switch will rotate the remote indicating compass card to the right. Okay, there you have it. All right, let's get to another topic. Down to instrument errors. We take you back to your classroom for a discussion of that topic.
While the flight instruments are generally very reliable, they do sometimes fail. It's therefore very important to understand these potential failures to maximize flight safety. To understand instrument errors, we must first understand the pedostatic system. Pedo pressure, or impact air pressure, is sensed through an open-ended tube pointed directly into the relative wind flowing around the aircraft. This pedo tube connects to pressure-operated flight instruments such as the ASI, or airspeed indicator. The pedostatic system provides sensors for the altimeter, vertical speed indicator, and the airspeed indicator. Other instruments depend upon accurate sampling of the ambient still air atmospheric pressure to determine the height and speed of movement of the aircraft through the air, both horizontally and vertically. This pressure, called static pressure, is sampled at one or more locations outside the aircraft. Now, on some aircraft, the static pressure sensor, which you can see right here, is sensed through flush ports on the side of the fuselage or the vertical fin. These ports are in locations proven by flight tests to be in undisturbed air, and they are normally paired, one on either side of the aircraft. This dual location prevents lateral movement of the aircraft from giving erroneous static pressure indications. The pitot tube receives ram air pressure or impact pressure, which is the result of air striking the airplane as it moves forward. This ram air pressure moves up into the airspeed indicator. Now we're also getting information from the static port, which provides the source of air pressure from the ambient air outside and around the aircraft. Ram air pressure is being received by the pitot tube and measured by the airspeed indicator, and the ambient air pressure is being picked up by the static port. It's the difference in these two pressures that shows up as an indicated airspeed on your airspeed indicator. So here's a quick summary. A static port is the source of ambient pressure. Pitot tube provides ram pressure for airspeed indications. Vertical speed indicator, or VSI, measures rate of climb and descent. And the altimeter measures the static air pressure and indicates height above sea level. Okay, back to instrument errors. Check this table. In the event the pitot tube becomes blocked, say by a bug, dirt, or some kind of debris, you'll not get an accurate indication with the airspeed indicator. Instead, this instrument is going to read 0. The altimeter and VSI will work properly. With a blocked pitot and drain hole and an open static condition, the airspeed indicator will be high in a climb and low in a descent. Again, the altimeter and VSI will function correctly. If the static source is blocked and the pitot is open, the airspeed indicator will indicate low in a climb and high in a descent. Both the altimeter and VSI will be frozen. When the alternate static source is on, the airspeed and altimeter will read high and the VSI will show a momentary climb. Should the VSI glass be broken, the airspeed and altimeter will read high and the VSI will indicate in the reverse direction.
Okay, let's cover a review question under this topic. If both the ram air input and the drain hole of the pitot system are blocked, what reaction should you observe on the airspeed indicator when power is applied and a climb is initiated out of severe icing conditions? Which of these is correct, A, B, or C? Your correct answer is C. If both the ram air or pitot input and the drain hole of the pitot system are blocked and no change until an actual climb rate is established, then indicated airspeed will increase. All right. Good enough. Let's tackle something new. Our next topic, instrument skills. And we send you back into the classroom for that one.
Instrument flying proficiency is the single most fundamental skill to ensure a safe and enjoyable flight.
Roger, I'm climbing through 2,300 for 5,000, 9 Golf Romeo.
November 9 Golf Romeo, that matched up a little bit better. You are radar contact 1 mile northeast of the Aurora State Airport. Turn left direct Newburgh on course.
Roger, turn left direct Newburgh on course, 9 Golf Romeo.
You can have all the best instruments and electronics in your panel, but without these skills, you'll not be able to be proficient and competently conduct your next flight. During attitude instrument training, the pilot must develop 3 fundamental skills involved in all instrument flight maneuvers. These are instrument cross-check, instrument interpretation, and aircraft control. When executing an ILS approach, the pilot must keep the aircraft on the electronic glide slope. This requires the ability to establish the proper rate of descent for the ground speed. As ground speed increases, the rate of descent required to maintain the glide slope must be increased as ground speed decreases. The rate of descent required to maintain the glide slope also decreases. By first cross-checking the instruments and then interpreting them, the pilot is able to precisely control the aircraft all the way to a successful landing.
Okay, let's take a look at a couple of review questions for you. What is the first fundamental skill in attitude instrument flying? The first fundamental skill, A, B, or C? Your answer is B. The first fundamental skill involved in all instrument flight maneuvers is instrument cross-check. Okay, moving along to the second question. The rate of descent on the glide slope is dependent upon which of these? Your answer is C. The vertical speed required to remain on the proper glide angle is dependent on the ground speed when flying on a fixed glide slope. Okay. Answers to a couple more questions, moving to a new topic. Attitude flying. Let's take that one into the classroom for you.
So far, you know that the attitude of an aircraft is controlled by movement around its lateral or pitch, longitudinal or roll, and vertical or yaw axes. In instrument flying, attitude requirements are determined by correctly interpreting the flight instruments. Instruments are grouped as to how they relate to control, function, and aircraft performance. Attitude control is discussed in terms of pitch, bank, and power control. The three pedostatic instruments, the three gyroscopic instruments, and the tachometer or manifold pressure gauge are grouped into the following categories. The pitch instruments are the airspeed indicator, the altimeter, plus the attitude indicator and the vertical speed indicator. The bank instruments consist of the attitude indicator, followed by the heading indicator, next the turn coordinator, and the magnetic compass. The power instruments include the airspeed indicator, the tachometer, and the manifold pressure gauge. The instruments which provide the best information for controlling the aircraft in any given maneuver are referred to as primary instruments. These are usually the instruments that should be held at a constant indication, which means you look at these first. The remaining supporting instruments should help maintain the primary instruments at the desired indications and be used as backup. When climbing and descending, it's necessary to begin level off in enough time to avoid overshooting the desired altitude. The amount of lead to level off from a climb varies with the rate of climb and pilot technique. If the aircraft is climbing at 1,000 feet per minute, it will continue to climb at a decreasing rate throughout the transition to level flight. An effective practice is to lead the altitude by 10% of the vertical speed. 500 feet per minute would have a 50-foot lead. 1,000 feet per minute would have a 100-foot lead. The amount of lead to level off from a descent also depends upon the rate of descent and the control technique. To level off from a descent at descent airspeed, lead the desired altitude by approximately 10%. For level off at an airspeed higher than descending airspeed, lead the level off by approximately 25%. When making initial pitch attitude corrections to maintain altitude during straight and level flight, the changes of attitude should be small and smoothly applied. As a rule of thumb, for airplanes, use a half bar width correction for errors of less than 100 feet and a full bar width correction for errors in excess of 100 feet. The FAA tests for 10 standard flight scenarios. These are as follows: straight and level, changing airspeed straight and level, adding power, constant airspeed climb, stable airspeed climb and descent, enter constant rate climb and descent, stable constant rate climb and descent, transition into a standard rate turn, maintaining a level standard rate turn, airspeed change level standard rate turn, and lastly, climbing or descending standard rate turn. While these flight scenarios may seem somewhat daunting, with a little experience, pilots will quickly learn these without having to use rote memory. As you gain experience, these scenarios will become second nature to you. As each scenario is presented, note the highlighted instruments indicating which are primary and which are supporting. Okay, here's the first scenario. Okay, we're going to walk through these scenarios. Now, primary for straight and level pitch instruments is our altimeter, and supporting instruments in this case are the vertical speed indicator and the attitude indicator. The next one that we've got is our straight and level bank instruments. Now, for straight and level bank instruments, primary is our heading indicator, and supporting would be our attitude indicator and our turn and bank coordinator. Let's take a look at another one. The next one we've got is straight and level for power instruments. Now, in this case, primary would be our airspeed indicator, and supporting would be our power instruments, manifold pressure and RPM. Our next scenario is straight and level summary. And in the summary, we have two columns, primary and supporting. Primary for pitch is altimeter, supporting for pitch is attitude indicator and VSI. Primary for bank is the heading indicator, and supporting for bank is the turn coordinator and the attitude indicator. Primary for power is the airspeed indicator, and supporting for power is manifold pressure and RPM. Okay, here we've got another scenario. We're talking about changing airspeed straight and level pitch instruments. Primary is our altimeter, and our secondary is our vertical speed indicator and our attitude indicator. In our next scenario, we'll take a look at changing airspeed straight and level bank instruments. Our primary is our heading indicator, and our supporting is going to come from our attitude indicator and our turn and bank coordinator. In a new scenario, we'll take a look at this one that's coming up, and we're going to look at changing airspeed straight and level. Manifold pressure and RPM are primary for changing airspeed straight and level in our power instruments, and our supporting information comes from our airspeed indicator. Now, take a look at this summary. The changing airspeed straight and level, again we have our two columns, primary and supporting. Primary for pitch is altimeter, and supporting for pitch is attitude indicator and VSI. Primary for bank is our heading indicator, and supporting for bank is our turn coordinator and our attitude indicator. Primary for power is manifold pressure and RPM, and supporting for power is our airspeed indicator. Now, our next scenario is add power and enter constant airspeed pitch instruments, and primary is from our attitude indicator, and supporting information comes from our airspeed indicator over here and from our vertical speed indicator. In our next scenario, we're taking a look at add power and enter constant airspeed bank instruments, and our primary comes from our heading indicator, and our support comes from our turn coordinator here. And we're going to take a look at the next scenario. In this one, we have add power and enter constant airspeed with power instruments. Primary comes from manifold pressure and RPM, and supporting comes from our airspeed indicator. Again, we've got a summary for add power and enter constant airspeed. Our primary and supporting columns. Primary information comes from pitch from the attitude indicator, and supporting pitch comes from airspeed and VSI. Primary bank comes from our heading indicator, and supporting bank comes from our turn coordinator. Primary power comes from manifold pressure and RPM, and supporting power comes from our airspeed indicator. In this scenario, we've got stable airspeed, climb and descent pitch instruments. The primary information is going to come from our airspeed indicator. Supporting information is going to come from our vertical speed indicator here and from our attitude indicator. In our next scenario, we're going to take a look at stable airspeed, climb and descent bank instruments. Our primary is going to come from our heading indicator. Our supporting information is going to come from our attitude indicator and from our turn coordinator. Okay, let's take a look at stable airspeed, climb and descent, power instruments. In this case, the primary information comes from manifold pressure and from RPM, and our supporting information comes from our airspeed indicator. Again, we have a summary of what we just took a look at. Stable airspeed, climb and descent, primary and supporting. Primary for pitch is airspeed indicator. Supporting for pitch is attitude indicator and VSI. Primary for bank is our heading indicator. Supporting for bank is our attitude indicator and turn coordinator. Primary for power is manifold pressure and RPM, and supporting for power is our airspeed indicator. Now we've got another scenario where we're taking a look at entering constant rate climb and descent for pitch instruments. Primary is going to come from our airspeed indicator, and supporting is going to come from our attitude indicator here. Also from our vertical speed indicator. In this section, we're going to take a look at entering constant rate climb and descent for bank instruments. Now our primary here has to come from our heading indicator, and support has to come from our attitude indicator and from our turn coordinator. Now we're taking a look at entering constant rate climb, descent for power instruments. Our primary is going to be manifold pressure and our RPM, and our support information is going to come from airspeed indications. Let's take a look at our summary for entering constant rate climbs and descents. Our primary information for pitch comes from our airspeed indicator, and our supporting information comes from our attitude indicator and VSI. Our primary bank information comes from our heading indicator, and our supporting bank information comes from our attitude indicator and turn coordinator. Our primary power information comes from manifold pressure and RPM, and our supporting power information comes from our airspeed indicator. In this scenario, we're taking a look at stable rate climb and descent pitch instruments. Our primary information comes from our vertical speed instrument, and our secondary information or supporting information comes from our attitude indicator here. In stable rate climb and descent bank instruments, primary information comes from our heading indicator, and our supporting information comes from our attitude indicator, also from our turn coordinator. In stable rate climb and descent power instruments, the primary information comes from our airspeed indicator, and our supporting information comes from manifold pressure and from our RPM. In this summary for stable rate climb and descent, primary for pitch is VSI, supporting for pitch is attitude indicator. Primary for bank is the heading indicator, and supporting for bank is attitude indicator and turn coordinator. Primary for power is our airspeed indicator, and supporting for power is manifold pressure and RPM. Now in this scenario, we have transition to standard rate turn pitch instruments. Our supporting our primary information comes from our altimeter, and our supporting information comes from our attitude indicator and also from our vertical speed indicator. In our next scenario, transition to standard rate turn bank instruments, primary information comes from our attitude indicator, and secondary information to supporting information comes from our turn coordinator. Transition to standard rate turn power instruments, our primary information comes from our airspeed indicator, and our supporting information comes from manifold pressure and RPM. Again, we have another summary. In transitioning to standard rate turn, primary information for pitch is from the altimeter, supporting information from pitch is for attitude indicator and VSI. Primary information for bank comes from our attitude indicator, and supporting information for bank comes from our turn coordinator. Primary information for power comes from our airspeed indicator, and supporting information for power comes from our manifold pressure and RPM. In this scenario, we're talking about maintaining level standard rate turns. Pitch instruments are going to come from primary information from the altimeter, and secondary or supporting information will come from the attitude indicator here and from the vertical speed indicator. In the next component, maintain level standard rate turn bank instruments, primary information comes from our turn coordinator, and supporting information comes from our attitude indicator here. And now we'll take a look at power, maintain level standard rate turn power instruments. The primary information comes from our airspeed, and our supporting information comes from manifold pressure and from RPM. In the summary for this section, maintaining level standard rate turn, primary information for pitch comes from the altimeter, and supporting information for pitch comes from the attitude indicator and VSI. Primary bank information comes from the turn coordinator, and supporting bank information comes from the attitude indicator. Primary information for power comes from your airspeed indicator, and supporting information for power comes from manifold pressure and RPM. In another scenario, we're going to take a look at changing airspeed, level, standard rate turn, our pitch instruments first. Primary information comes from our altimeter, and supporting information comes from our attitude indicator and from our vertical speed indicator. Changing airspeed, level, standard rate turn bank instruments, primary information comes from our turn coordinator, and supporting information comes from our attitude indicator, and also we're going to take a look now at changing airspeed, level, standard rate turn power instruments. Primary information comes from manifold pressure and from RPM, and supporting information comes from our airspeed indicator. In this summary section, changing airspeed, level, and standard rate turns, primary information for pitch comes from the altimeter. Supporting information for pitch comes from the attitude indicator and from the VSI. Primary bank information comes from the turn coordinator, and supporting bank information comes from the attitude indicator. Primary power comes from manifold pressure and RPM, and supporting power comes from airspeed. In this scenario, climbing standard rate turn pitch instruments, our primary information comes from our airspeed indicator, and our supporting information comes from our attitude indicator here, also from our vertical speed indicator. Climbing standard rate turns bank instruments, we've got it up for you in advance, and the primary information comes from our turn coordinator, and our supporting information comes from our attitude indicator right here. And then climbing standard rate turn power instruments, the primary information comes from manifold pressure and from RPM, and our supporting information comes from our airspeed indicator. For this summary, we're taking a look at climbing standard rate turn. Our primary pitch information comes from airspeed, and our supporting pitch information comes from attitude indicator and the VSI. Primary bank information must come from the turn coordinator, and supporting bank information must come from the attitude indicator. Primary power must come from the manifold pressure and RPM, and supporting power must come from the airspeed. Okay, that's a lot of scenarios. Now, when considering primary and supporting, ask yourself which factors apply. Which will be primary or supporting instruments? Is this a steady state or a transitioning phase? Consider each attitude, i.e. pitch. Which instruments provide pitch information?
Okay, let's take time for another review question. This one, the gyroscopic heading indicator is inoperative. What is the primary bank instrument in unaccelerated straight and level flight? Which of these is correct? Your answer is A, magnetic compass. The heading indicator provides the most pertinent banking information in unaccelerated straight and level flight, since banking means turning and it is primary for bank. With gyroscopic heading indicator failure, the magnetic compass becomes the only heading indicator. All right, let's move along. And our final topic in this lesson, unusual attitudes. Let's get back with your instructor in the classroom for that one.
When recovering from an unusual attitude without the aid of the attitude indicator, approximate level pitch attitude is reached when the airspeed indicator and altimeter stop moving and the vertical speed indicator reverses its trend. We'll begin with this scenario. Now, here are the attitude indications for nose high and climbing conditions and nose low and diving conditions. The following procedure is used to recover from a nose low attitude. Number 1, reduce power. Number 2, level the wings. And number 3, raise the nose to the horizon in level attitude. The following procedure is used to recover from a nose high attitude. Number 1, add power. Number 2, apply forward elevator pressure. And number 3, level the wings. Finally, here is an attitude indicator displaying level flight. The altimeter rate has slowed. The airspeed change has slowed, and the VSI direction is reversed.
Okay, let's take a look at 2 final review questions for our final topic in this lesson. We're going to ask you to refer to a figure in just a moment, but our question is, what is the flight attitude? A given here is that one instrument on this figure has malfunctioned. What is the flight attitude, A, B, or C? We'll come back to that, but first take a look here. The attitude indicator indicates a level turn to the left. Our airspeed indicates a decreasing climb. Altimeter agrees with airspeed indicator showing a climb. The climb indicator agrees with the airspeed and the altimeter. Turn coordinator shows a turn to the right, and the heading indicator shows a turn to the right. So which of these has failed? Well, the attitude indicator has failed. Going back to our question to determine the answer, what is the flight attitude? A climbing turn to the right. You're in a right climbing turn, thus we showed that the attitude indicator has failed. Okay, next up. Again, we'll ask you to refer to a figure. What is the correct sequence for recovery from the unusual attitude indicated? Okay, let's take a look at that figure for you. Here we have it. Now our attitude indicator shows a right turn. Our altimeter agrees with the attitude indicator. The rate of climb agrees with the altimeter. Heading shows right turn. Our turn coordinator shows right turn, which means pitot-static system has failed. Too much airspeed there. In order to correct that, what do? We 1, add power, 2, lower the nose, and 3, level the wings. So if we go back to our original question to ascertain the answer, well, it's B, add power, lower nose, level wings, return to the original attitude and heading. Well, there you have it for lesson number 3. Next up, what kind of backup instrumentation do technically advanced aircraft use should the screens go black?
Well, these technically advanced airplanes typically offer 3 conventional style gauges. It's an airspeed indicator, an attitude indicator, and an altimeter. The one thing I'd recommend to any pilot is get lots of regular practice using these things. Everyone thinks, well, these new systems are practically fail-safe and they only fail in 1 in 10,000 cases, but the thing you have to keep in the back of your mind is what if on some occasion you were today's lucky winner. So get lots of practice using everything in the cockpit.
Very good. Now, with no physical moving parts or electrical circuits to follow, how should a pilot go about getting familiar with the systems that are associated with cockpit automation like GPS?
Well, I see 2 challenges here. One is mastering what I call the knobology, is just learning what button pushes and dials are required to use the thing. And that's something that just takes a little bit of practice. After a few hours, your fingers know the way around the cockpit. The second and possibly more important one is learning to understand what the systems are doing. You don't ever want to be in a case where you're just simply pushing buttons and the only thing you understand about what's happening is that the computer will take care of it. That's a bad place to be. To me, this is the difference between being a pilot and a passenger.
Steve, how do pilots avoid becoming complacent in a cockpit filled with computers?
Yeah, I think this is the most challenging part of becoming proficient in an automated cockpit. And we've seen this in one study after another, where pilots tend to drift back and fall out of the loop once they've become comfortable with using the systems. And I'd have to say that this is absolutely the wrong approach to take. Why? Because these computers might not always be doing what you think they're doing. The approach I take is to sort of consider the automated systems as maybe something like a mid-time instrument student. It seems to fly the plane okay, but you need to keep your eye on what they're doing and make sure the right things are happening at the right times.
Now, you've probably, Steve, probably got some recommendations to pilots, ways to automate their current cockpit. What would you recommend?
Well, for the pilot that's adding one system at a time to their cockpit, I would just say start out slowly. Take the time to get to know each system, how it works, and how to integrate it into your everyday way of doing things.
4.